In this video, we're going to begin talking about measurements and physical chemical properties. We're going to focus on how scientists measure things and how they keep track of those measurements and how to do some calculations. So this first slide is just kind of a funny thing with the metric system versus the imperial system. In chemistry, most of the time we're working with the metric system. It's a standardized mechanism for measuring, and if you use it enough, you become familiar with the simplicity of that system. But here in the United States, a lot of things are in the imperial system. We use feet, we use miles, we use things that are not standardized as well as the metric system. But most of the time in chemistry and in the chemistry lab spaces, we'll be using the metric system. To begin this discussion about measurements, I first want to talk to you about the different ways that we can make observations, right? So science is about observing and measuring and taking note of those things to be able to make predictions at some point. So the first part of this is to look at the observations, and they can fall into two different categories. We have quantitative observations, and so quantity is in part of this word, quant, and that means that we're measuring numeric data. So there's a number involved, right? And there's a measurement usually using some type of instrument. So we're going to use a thermometer or a scale or a ruler, for example. And these are some common examples of a quantitative measurement. Qualitative observations do not involve numerical observations. For example, the color, rapid boiling, a solid forms. So something that happens that you observe, but you don't necessarily write a number down. So these are the types of observations. There are really two types. You can see here on the left, here is actually a Western blot. So we're looking at protein levels of two different types of treatments here. And we don't have to go into great detail, but I just want to show you kind of the difference. We can look at this and create qualitative observations like, oh, looks like this protein is found in this PBS version, but then with this alpha SWNT, it seems to go away. I don't have a figure legend, which would obviously be helpful for you to understand more what's going on here. But we can make some observations like, oh, beta-actin's always there, and DCX kind of goes away. So we can make some qualitative observations, but we can also turn some of these things, sometimes we can turn these into quantitative observations, where we can see now here on the y-axes are arbitrary units. So this is measuring each of these little spots here, or actually if you're averaging them, you're getting an average of these, and you're able to kind of maybe a little better see some of the trends and things that are happening. And we can also do some statistical analyses when we do this. So sometimes you can take qualitative observations and turn them into quantitative observations, so we can use some mathematical principles on those. But just the introduction of the types of observations that chemists typically make. When we are measuring things in the lab, there's always an involvement of estimation and uncertainty. And there's always some reference that we're taking it against. And so that means that when here we're looking for a measurement, it always involves a comparison. So we always have a reference point that we're comparing it to. And so that is where we get a number and then a unit. So let's go back to that last example quick, and you'll see that with this Western blot, so you don't necessarily have to have known what a Western blot is or what these things are. But what I want to tell you is that this beta-actin, this is a protein in all of the cells of your body, and it's just always there. So this is actually acting as a reference for this Western blot analysis. And you can see it's kind of relatively the same each time, and it should be. That's the expectation. Over here, it's arbitrary units. So these are typically done in using this as a reference, as a standard. So if you have as much beta-actin as your, for example, one of your treatments, that'll be the same number. And if you have less of that thing than you have for the beta-actin, then that will go down. So we're using this as a reference so we can understand how things are changing or where they are relative to that reference. So that means for most types of observations that involve measurements, we are going to be measuring things with units. And that means if we're going to measure a length, we're going to be in meters. If we're measuring a weight, that's going to be in kilograms. If we're measuring a volume, that might be in liters or milliliters, right? So we have a unit associated with that. And the other thing that I mentioned earlier, there's always an uncertainty. There's never an exact amount that we're going to have. There's always estimation. Again, going back to this slide, right, we can kind of generate an estimate here. You can kind of look at the darkness of pixels. That's generally how these are created. But there's some uncertainty, right, because this is a lighter background. This is kind of more gray. This is darker. So that might change some of your results. So there's always some uncertainty. There's always maybe, because these are kind of crooked a little bit, you might cut a little, make a little area that's not quite the exact size of where your stain is going to be. So there's always some uncertainty. There's a limitation from the instrument or the person that's using that instrument. For many of the kind of uses in lab where you'll be taking measurements, there are a typical international system of units that are recognized, and these are, again, the metric system based off of using the meter for length, kilogram for mass, seconds for time. So these are just some of the common ones, although we'll use some in chemistry that maybe are not using the international system. So this is the base units. We'll use some that might be different depending on the amount, right? So if you're in the lab, for example, you might not be measuring things in kilograms. You might be measuring smaller amounts in grams, for example, and that's fine. But there's a system for doing this, and these things can be easily scaled because of this, how we use the 7 base units, and we'll show you that in a second. All of those base units, we can look at all of the different physical properties and quantities and units derived from 7 base units in terms of length, the distance, or the size. For example, area, we're looking at length versus width, or meters versus meters, so we get meters squared. So these, we can generate all of these from these basically other 6 forms that we looked on here. All of these are kind of the basis for that, and then from these we can generate anything else that we'd want to measure. It's kind of an interesting thought. So again, the units, something to notice, right? We have 2 meters. If we're doing the area of something, we're looking at the length and the width of this area. We're going to take meters times meters, and we get meters squared. So something we're going to have to notice is that when we are taking into account, when we're measuring things, when we do things mathematically with them, the mathematical operation follows along with the unit as well. So that's an important distinction. These are some non-systematic, international systematic metric units that are used. A lot of times if we're looking at really small things, if we're looking at protein structures, for example, a lot of times those are going to be in angstroms. If we're looking at atomic mass units, so we haven't talked about those perhaps yet, but maybe we're looking at how many protons or neutrons or electrons are found, and we're going to be using the atomic mass unit to define that. A lot of times metric tons, we're looking at minutes or hours, so it just depends on the scale that you're most comfortable with. We also use Celsius instead of Kelvin oftentimes in the chemistry lab because that is what our thermometers are calibrated to, and liters instead of, for example, we in the systematic unit for, we don't necessarily for length, it would be meters cubed would be for volume, but instead we typically use liters in the lab space instead of meter squared, for example, or cubed, for example. So one important thing is that, remember, when we measure things, we're using a standard. So if someone's using a different standard than someone else, then you can have differences in the numbers that you're getting. For example, if we have inches or yards or miles, those are all units of length. but you'll notice that they are equal to different amounts. There's a different unit, there's a different standard for each of these. So 1 inch is equal to 2.54 centimeters, or 1 yard is equal to 0.9144 meters. So these all can be converted from one to another. Now there's always an app for that, but I'm going to talk to you about some tricks on how to easily convert. And this is actually going to be important that you understand how to do conversions without using an app, because when we get further into the semester, we're going to have to do things that maybe have more complicated versions or units than just kind of one-to-one here. So we're going to be having to do things that are going to be a little more complicated when we start adding on units to things. For example, we're looking at density, which is grams per volume of substance in a volume. So that's going to change now how we're looking at these, and it gets more complicated. So I'm going to teach you some tricks on how to do some conversion. Certainly there's an app for that, but sometimes we use these units to solve problems, not just to convert from one to another. So this is kind of one of those things in chemistry where you might have learned it one way, and I might teach you a different way on how to do something. And it's important that you understand how I'm doing it here, even though you maybe have done this in the past in another class or with another person, another teacher. But it's important that you learn my way of doing this as well, because I'm going to teach you how to do other things with that maybe you haven't done yet. So this is part of kind of the mental exercising of your brain for chemistry and for the things I'm going to teach you. So please, even if you have done this in the past and you've done it a different way, please follow the directions and the way that I'm doing it, so that you'll be able to solve the problems that I'm going to give you on exams and give you in the future in here. So of course, when you are in real life measuring something, right, you're not going to necessarily use the systematic unit, right? The systematic unit for length is meter, for example. But if we're doing something in the chemistry lab, a lot of times we're not measuring things in meters because it's way too big for a chemistry lab. So a lot of times we're going to be using centimeters, for example. And a centimeter is equal to 0.01 meters, or a millimeter, which is 0.001 meters. So this is why it's actually pretty easy to make these conversions in metric versus the imperial system, where you have feet and then they go to inches, but they don't come down, and just basically it's simple because you can just use and move decimal places with the metric system, which is very nice for simple and quick calculations. So we use prefixes for the SI base units when the number's too large or small. So looking at this here, we have the difference here. Right here is the line where we're talking about, a standard compound. And when things are going to be bigger, maybe if we're in grams, we might use, or actually, let's go into data, right? So if you have a byte of information, right, we also, when we get bigger, we might have a kilobyte or a gigabyte, a terabyte. Those are kind of the amount of space on our hard drives, for example. We get bigger and bigger and bigger. We're going to maybe someday have petabytes of hard drive space, or exabytes of hard drive space. So a lot of times we look into, we want gigabytes. When back in the day when I was in college, we'd be happy to have a gigabyte of data, right? And now we want a terabyte of data is a good size memory for a computer. When we get smaller and those things get tinier and tinier, for example, if we're in grams, if we're measuring things out, we have kilograms. That's a lot of stuff. People mostly weigh themselves. If you're using the metric system, you'll have kilograms of weight typically instead of pounds, what people weigh themselves in. But if we're measuring smaller and smaller things, we're looking at smaller than a gram, or we're looking at very small amounts of a substance or a chemical, we might go into centigrams or milligrams, micrograms, nanograms. So we are looking more closely at these amounts for smaller things. And so it's just a matter of how we're measuring things and what we're doing with them. So how do we use these things? Well, for example, if we have 1 milliliter, that is equal to 10 times the negative third in meters. So 10 to the negative third, let's look at, we have to also kind of talk about what this means. So 10 to the negative third means that we have a unit here that is smaller. We're going to put the decimal place negative 3 spots. So we have a 10. I'm going to just put this on a decimal point in there. So there's a third digit. And we're going to move this decimal place to make it smaller, right? If we have a negative 3 here, that means the actual number. This is scientific notation, and this is a simplified way of writing this out. But if we want to actually write the number that it represents down, I'm going to start here. And if we're going to subtract 10 units from the decimal place, or 3 units from where the decimal place is, I'm going to move over 1 time, 2 times, and 3 times. So I have a decimal place here. That means I have to put a 0 here. We always put a 0 in front of that number as well, just so that's clear when you're writing it out. Sometimes it's hard to see if I write, for example, like a little dot here, 0, 1, 0. You might not see that dot, and then it's confusing. But if you put a leading 0 in, then it's very clear that this number is actually going to be 0.010, right? So that is these are equivalent to each other. So you're going to be practicing some of these just to convert things from the scientific notation back and forth, and this should be pretty simple to do after you have some practice with that if you've not done it already. Some other examples: 1 kilometer or kilometer is equal to 1,000 meters. 1 nanograms, 1 times 10 to the negative 9th grams. If we go back to that last slide, where nanogram, right? So 1 gram is equal to 1 times 10 to the negative 9th grams. So if we move this decimal place over, 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's where it's 1 billionth of a gram, for example. So these are different ways that we can do that. Here we have 1.13 times 10 to the 6th meters is equal to 1.13 megameters, essentially. So we can use these to convert from one unit to another. We use these these multipliers, and notice what we're actually changing is, so from this first part here to here, we are turning this into scientific notation. But from here to here, we're just using these conversion changes in the value multipliers, right? So we're just changing that from a meter to a megameter to say, oh, this is actually this unit. It's kind of the same thing. So this is something that we do in chemistry to make these numbers, to kind of simplify these numbers, and to use units in the kind of range or the scope that we're looking at them in. So it would be kind of, if we're always looking at things that are 1,000,000 meters long, and we're going to keep looking at numbers this big, it's easier than just say, instead of 1,130,000 meters, it's just easier to say 1.13 megameters. So that's why we do that, and it's common with chemistry. We're often going to be looking at concentrations of chemicals, and they might be millimolar, or we'll use those terms. So getting comfortable with these conversions, getting comfortable with scientific notation is part of understanding that language of chemistry. All right, so going back to this figure, what is it that you notice about these multipliers? So one thing that you may notice, if I take some of these out in the middle, is that when we're looking at some of these, a lot of times they're going to go up by 3. So the most common ones anyway. Obviously, right, you might have heard of centimeters or decimeters. Hecto, maybe not. Deca, perhaps not. So those aren't as common as the ones that go up by threes, groups of three. So we'll move this by basically in the thousands. We'll move them in groups of three, and these are the most common. So milli, micro, nano, pico, these are the most common. When we get smaller, when we get bigger, kilo, mega, giga, which I'm sure you've heard in terms of bytes anyway, terabytes, petabytes, exabytes. So these are all getting bigger by value powers of three, and these are getting smaller. So these are some that you should know, at least milli, micro, nano, especially on the smaller size. We're not going to get into, at least most chemistry labs don't get into the picos unless we start talking about some typically, usually, or not. So these three and these three, you should have a good handle on these and practice some problems using those. And we'll talk about them quite often this semester. So the systematic unit for volume is technically meters cubed, right? It's the length three ways, the width, the height, and the length. However, because rulers are not very useful for measuring liquids, typically we'll be using graduated cylinders, burettes, pipettes, or volumetric flasks. And in a lab space, these are some of the common chemistry tools that we use for measuring volumes. More commonly, we're going to measure things in liters or milliliters. And so 1 liter is equal to 1 decimeter cubed. So these are exact conversion factors, but we'll mostly be talking in liters. And also milliliters, which is 1,000th the size in unit, right? So 1,000 milliliters is equal to 1 liter. This is another common form that's used, and that's equal to 1 centimeter cubed. Moving on from volume to mass, the systematic units in kilograms, as I mentioned earlier, we typically, if you're weighing yourself in your mass in the metric system, it's typically in kilograms. We'll commonly in the chemistry lab space use more grams just because it is a smaller amount, and typically when we're doing chemical reactions in the lab space, we use smaller amounts, and it's mostly commonly used in grams unless we're scaling huge reactions up. A kilogram is 1,000 grams, and 1 gram is 0.001 kilograms. So kind of using those conversion factors that I had showed you earlier. If we want to measure temperature, you've seen this before, we have 3 different scales, Fahrenheit, Celsius, and Kelvin, and these are all related to each other. We have mathematical equations to convert these. We're not going to talk too much about converting Fahrenheit to Celsius. Again, there are enough calculators to do that, and also between Celsius, Fahrenheit, and Kelvin, but these are typical scales that are used. So Fahrenheit is typically used in the US, and the units that are used where it happens, it was kind of arbitrary, and just so happens that water freezes at 32 degrees Fahrenheit, boils at 212, and there are 180 degree units between melting and boiling points of water. So someone decided, if we're going to do more of a systematic method, some common way and a good way to be able to calibrate these things will be to look at the freezing point and the boiling point, and to more systematically make these easier to read. So if we have the Celsius scale, actually more commonly used in science, it's helpful that water freezes at 0 degrees Celsius. It boils at 100 degrees Celsius, and there are 100 degree units between those points versus the 180 degrees. So these don't easily convert between each other. There's a little more complex way to convert those, and we're not going to go into detail about that, but there are, again, apps or ways that you can easily convert from Celsius to Fahrenheit if needed. The Kelvin scale, there's actually not technically a unit for that. So there's no degree, sorry, that's still a unit, but there's no degree symbol. So it's just 273.15 Kelvin. It's not degrees in Kelvin, it's just is Kelvin. And there are 100 points between melting and boiling points. The only difference between Kelvin and Celsius is that the scale is 0 point. So the lowest unit in Kelvin is 0. The lowest unit in Celsius can go well below 0. So absolute 0 is the 0 point on the Kelvin scale, and it corresponds to nature's lowest possible temperature, where nothing's moving, there's no energy in the system, and that's where the 0 point is set at. So I want you to look at this chart, and there's the 3 different scales. We have Fahrenheit, Celsius, Kelvin, and just think about why this is a funny joke if you like dad jokes. I mentioned I didn't want to go into excruciating detail about this, but if we're at 0 degrees Celsius, where water freezes, 32 Fahrenheit, that's 273 Kelvin. So basically, to convert between Celsius and Kelvin, you just add 273 degrees. From Fahrenheit to Kelvin is a little more complicated, but we'll just do, this is kind of the conversion. If I'm in temperature Fahrenheit to temperature in Celsius, we add 32 degrees and then 9/5, because remember we had 180 degrees in that between 0 and 2, basically between the freezing and boiling points, and then but in Celsius it was only 100. So that fraction is kind of that distinguishing difference between those amounts. So I'm not going to have you memorize this or anything, but just an example, 100 degrees Celsius is how many Fahrenheit. You basically plug in that Celsius value and then solve for Fahrenheit. This isn't something I want to focus on in this class because it's not a typical conversion factor where we're going to use my method I'm going to show you in a moment. So when we're looking at measurements, remember I mentioned earlier that all measurements are inexact, which means that even if you have calibrated instruments or you're doing appropriate lab technique or you're doing the method correctly, there can still be errors in the measurement. Just the limitations in the instrumentation can sometimes cause this. So the ways to minimize errors, and this is an analytical technique that's oftentimes used in a lot of different areas of science, not just chemistry, but ways to minimize these errors is to take a series of different measurements and then to calculate averages and mean values and doing some standard deviation things. So these are ways that we can get around those issues. So here is just an example of doing this. If we're looking at 2 different Celsius-based thermometers, and on the left, the thermometer has markings every 1 degree Celsius, but on the right, the thermometer has a marking every 0.1 degrees Celsius. So you can see here, if we look and we estimate this, we have 21, 2, 3, 4, and we can always estimate that last value. So it's between 24 and 25, so I'm going to say 24.3. Okay, so there is an estimate at the end, and that's how it's always going to be. Whether you're using a thermometer or a scale, you might notice you put something on a scale and it'll kind of go between 0.1 or 0.2 grams, and that last one's always kind of back and forth, and you're like, oh, it's broken, it's not taking the measurement. It's just because that last measurement is always, this last value that's put down is always an estimate. So that's something to know about the way and the limitations. So if we're looking at the right thermometer, we can see 24, and the next big written out number is 25, right? So where we have multiple things and we go from 20 to 30, this is 1 Celsius unit. These are 0.1 units. So I can look at 24, 24.1, 0.2, 0.3. So 24.3, and then I'm going to say 0.32. Maybe you would say 0.35. So if we actually look at this zoomed in version, you know, it's not quite halfway, it would be about here. So I'm going to estimate 0.32. Notice that the difference in the tool that we're using, how close those units are fine those markings are allows us to get a more precise reading. And you'll notice that again, that last digit is still an estimate. It's a guess. And that's why we have a plus or minus here. We're just saying, okay, so that last marking is a guess, and that we're going to just guess there. So this is where we come to what's called significant digits. And a significant digit's that last kind of guess. We have 3 significant digits here, 1, 2, 3, versus 4 significant digits. The number of significant digits tells us how precise our readout can be. So I want you to take a second. Here is a graduated cylinder. Estimate what you think that volume is, and then so you can pause and just do that, and then unpause, and I'll talk about it. So when we're reading volumes from these types of instruments, we always want to read from the bottom of the meniscus. So if you said 51, 2, 3, you were not quite correct because it was less than that. You can see the meniscus is under that 53 mark. And then we always have to estimate that last digit. So it's going to be 52 point, for example, 8. And again, it's that last one's an estimate. So we know that there's a little bit of error in that last readout, but we hope that it's 52, that one is correct. I mentioned digital displays a lot of times with balances. We will see that. If we put a beaker on here, on the scale, it might say 65.2 grams, but that last number is still uncertain. So we're assuming anytime you use a scale that last number, you might have 0.0000. That means that you have a more precise scale, but that last number is always a guess. So you assume that last, assume half in that last readable digit there. So you would record this on a scale, even though it says 65.2, you put 65.20 plus or minus 0.05. So it could be 65.15 or 65.25, and that shows that you have some error in that last digit. Okay, so this is a little side about accuracy and precision. I have been using some of these terms, but I just want to make sure that we are on the same page for using both of these and when to use them. So here are 3 different examples of accuracy and precision in use. So accuracy is the measurement of how close is that measurement to the true or accepted value. And so we look at the measuring device has to be calibrated with that reference that we talked about earlier a few times to give that correct value. Precision, on the other hand, is how well a set of repeated measurements of the same quantity agree with each other. So and again, the more significant figures will allow for more precise measurement. So the more gradations between units, the easier it is to be precise. So here's a golfer being precise, right? We have precision, repeated measurements are the same, but inaccurate because we want that spot where we are landing our balls, we want that to go in the hole. Here is inaccurate and imprecise, so those balls end up being separated by quite a distance, and they also are not going where we want them to go. And here is accuracy and precision, where we get all 3 golf balls in the golf hole. They're grouped together, and the final measurement readout's the same. So there is a term called significant figures or significant digits. And these are telling us how precise our instrument can be. And if we look at these 3 different scales, we'll notice that this first scale can have 4 digits, right? And 1 after the decimal point. This scale, we don't necessarily know, it might be able to have more, but it has 3 digits after the decimal point. And then this scale over here is 1, 2, 3, 4, 5. So if we go from least precise to most precise, it would be from left to right. And we can tell precision based on the number of digits after the decimal place. So what are the maximum significant digits you could get with each of these if you're going to weigh out approximately 5 grams? So the answer for this one is we get, if we only are measuring 5 grams, right, we're not going to get the 4 digits on here. We're actually going to get 5.0. And so this would have 2 significant digits. If we go to the next one, we would have 5.000. So we would have 4 significant digits. And finally, in this last case, we would have 5.12345 zeros following. So a total of 6 digits, a total of 6 significant digits. So here we would have 2 significant digits, 4 and 6. What about if we weighed out 0.05 grams? In the first scale, we wouldn't be able to really get anything, right? Because that scale doesn't measure down to 0.05 grams. So we might get a 0.1 in there, but it's not going to be really give us any digits, likely not any digits. So maybe up to 1 if it happened to measure like 0.1 on there. For this second scale, if it's 0.05, we would get 2 digits because we would have the 5 here and the 0 here and the 0 in front of the 5, the point. So we would count 2 significant digits, and then with this final scale, we would get the 5,000 to measure out. So we would get 4 significant digits here. So let's talk a little bit more about significant digits and how to do that. So this is a simple, and again, this just tells us about the precision of our instrument, this idea of significant figures. So the idea of significant figures is to have a convention, a way that everyone's going to handle numbers in the same and consistent manner so that we can get and understand the precision of our instruments. So this is something that we're going to talk about, I'll have you do a few practice problems. These will be some questions on quizzes or exams on significant figures. And it's just an idea of, in the real world, when you're taking measurements, there are numbers that are associated with those measurements and units associated with those measurements, and they mean something. They tell us something about how those data were collected. So for scientific convention, all digits and measurements up to and including the first estimated digit are significant. So this is what we call significant figures. And digits in measurements from first non-zero number on the left to the first estimated digit on the right are considered significant. So let's just practice this with an actual example. So how you measure the whatever it is, the water, the length, the weight, how you measure that will dictate the number of significant figures that you'll end up with. So for example, if we have a burette, burettes typically have significant figures of 0.01. Their gradations between the units are by 0.1, and then you can estimate that last digit. For example, a graduated cylinder, we might have less precision, right? So we have just 0.1 between these digits. A volumetric flask, we have very good precision, but there's only one line on here. So it's not really great for measuring volumes outside of whatever the volume is for that compound. So this would be 0.01. And then a pipette would have usually pretty high precision as well. This one in this instance says 0.01. A lot of times it'll tell you the precision on the glassware somewhere. It'll give you this indication of the plus or minus of where that significant number will end up with. So I want to talk about some of the rules for significant figures. And if we're looking at these, how to determine if it's a significant figure or not, all non-zero numbers are significant. So anytime you have any number, in this example, 3.456, that has 1, 2, 3, 4 significant figures. So that's the easiest way, right? It gets trickier if you have zeros between non-zero numbers, or between non-zero numbers. So if we have 20,089, these zeros are significant. One way that you can simplify this and know if it's significant or not is to convert it into scientific notation. So we mentioned with scientific notation, you basically create one unit digit. So you just have one place in front of the decimal place. So in order to make this a scientific notation, we're going to move the decimal place from back here. We're going to count 1, 2, 3, 4. And so we have 2.0089. So this number is the same, except we move the decimal place 4 digits, and then that allows us to have times 10 to the 4th, so that tells us how many times we move the decimal place. Now it's easy to count, so now we know it's kind of the same thing. We'd have 5 digits, 1, 2, 3, 4, 5, or 5 digits here. Trailing zeros always count as significant if the number has a decimal point. And remember, the reason for significant figures is it tells us the precision of the instrument that we're using to measure it. So if we have 500 point, right? If you put a point at the end and you don't have another zero, that just means it's 3 digits, 3 significant digits, because it has a decimal point. Or you can write it in scientific notation, 5.00, and if there's a decimal point and you're putting those in there, then it would have 3 significant digits. If you just wrote 500 and you didn't put a decimal point in there, then it would actually only have 1 significant digit. So let's go on to some of these other rules. So this is where I just mentioned final zeros on a number without a decimal point are not significant. So here's 104,956,000. Or I can write this in scientific notation, right? I can move the decimal place up to here so that there's only 1 digit in front of the decimal place. 1, 2, 3, 4, 5, 6, 7, 8. That's where I get the 10 to the 8th. I get my scientific notation, and it's also now easy for me to count 1, 2, 3, 4, 5, 6. I have 6 digits. There's 6 significant figures. So if I don't put a decimal point here, then I don't count those as significant. Final zeros to the right of a decimal point are significant. So if I put 3.00, remember that tells us the effectiveness of the precision of the, for example, a scale that we're using, right? If that scale example we looked at where it had only 1 decimal places versus 2 versus 5, it's more precise. This measurement tells us something about the precision. So this example has 3 significant digits because it has a decimal point, and you count those digits behind the decimal place. Leading zeros to the left of the first non-zero digit are not counted as significant. For example, if you have 0.00012, you would move the decimal place for its scientific notation. You'd move this over to 1.2 times 10 to the negative 4th. 1, 2, 3, 4, right? We moved that 4 10 units over. This would have 2 significant digits. Again, writing these down in scientific notation can help you better identify how many significant figures you will see. Some other rules about defining significant figures are some special situations. For example, we have if you count something. If I'm just counting things, those are exact numbers. If we exactly count something, that's different than estimating, but if you count something, those are exact numbers, and they're exactly defined. They have unlimited significant figures. It's 250 and then 0.00000 forever, right? You don't count those in your calculations. They're exact. If you have conversion factors, those are exactly defined. 60 minutes is equal to 1 hour. Those have unlimited significant figures anytime we're converting one value to another. So I want you to take a moment and do this learning check. So take some time to practice some of these problems. I would recommend pausing here and just to make sure that you understand. If you don't understand or you can't get to the right to answers, then rewind a few minutes and re-look how we talked about some of the rules for significant figures. So practice this, write down an answer, pause it, and then I'm going to continue and I'm going to talk through some of the answers in a moment. But again, practicing these things, these are the kinds of questions you're going to see on quizzes and homework and exams, so it's worth taking some time if you're unfamiliar with these concepts. All right, let's take a look at some of these questions here in terms of finding the significant figures. And this first one, pretty simple. We just add up all the non-zero, all the non-zero numbers. We have 1, 2, 3, 4, 5. So we have 5 significant figures here. We can turn that into scientific notation. So again, if you haven't done this for these below, maybe a good way to practice doing this and to see if you understand how to do this properly, pause and try to write out scientific notation. I'll walk through that as well. This again is a helpful tool for understanding how many significant figures you'll have. We basically just want to have one digit in front of the decimal place to generate these. And then if this is a +2 here, we make that number bigger. If it's a -2, we would make that number smaller. So here we have 1, 2, 3, 4, 5 digits, still with scientific notation, and the number of significant digits is 5. For this second problem, again, we want to turn this, if we turn this into scientific notation, we need to go backwards with the decimal point. We have to move 1, 2, 3, 4 units backwards, which means that we're going to have to multiply this times 10 to the -4 because we're going backwards. This number is going to be is getting smaller when we do this. So 6 times 10 to the -4. Notice we don't have any trailing zeros. We don't count these. That was in our rules that I showed you previously. We don't count zeros in front of those numbers after the decimal place. So we only have one significant figure in this instance. For number 3, we can't change this into scientific notation. It's already in that same format. It's got one space in front of the decimal point already. And so all of these digits, any zeros in between numbers are going to be significant. So the total number of digits here is 7. They're all significant. Here we have 4, it's 161,000. Move this into scientific notation. We're going to take the decimal point that's not shown, but it would be here. 1, 2, 3, 4, 5. So you have one space in front of that, right? And there are 5. We're going to expand that to 5 decimal places. So here we are at 1.61. We don't include these in the discussion because there's no decimal place there. So we only have 3 significant digits. And finally, this one, we do have a decimal place here, so we're going to count all 4 of these. I'm going to also convert this into scientific notation by moving this 1, 2, 3 to 3.600. That, again, because we have that decimal place, it's telling us all of those are significant. And so we're going to count all 4 of those digits as significant. As you can see with that last kind of group of work problems, one of the clearest ways to unambiguously show the number of significant figures is by using scientific notation. So report numbers between 1 and 10 followed by the correct power of 10, and that indicates only significant digits. So an example of this, right, this is in practice. If we're going to estimate the number of people at a concert, we're saying, okay, it's about 75,000 people attended a concert. And we're saying that there's uncertainty, it's plus or minus 1,000 because we didn't put a decimal place here. We're just guessing at the number. If we change this into scientific notation, we move this to a number between 1 and 10. So we move this 1, 2, 3, 4 spots to 7.5. And we would make this number, to make it bigger, we'd multiply it by a factor of 10,000, 10 times 10 to the 4th power. But let's say we're looking at this in a different way, and the uncertainty is from an aerial photograph versus just kind of someone looking out from in the crowd. So here we might change this we might add a 0 in scientific notation to say, hey, we're more certain that we have a better estimate than this initial rough estimate. So we're going to always keep a single digit in the front. It's not generally always, it always happens. 7.5. You're not going to use 75 times 10 to the third. That's not scientific notation. And if you're going to do some rounding, sometimes this is going to happen. You're going to need to round digits if you're doing some mathematical equations. And typically there are different rules for doing this as long as you're being consistent or operating under what would be considered standard operating procedures in your lab or in the space that you're working in. A lot of times if the digit to be dropped is 5 or greater, you round up. So an example of this, 3.677, if we're saying there's only 3 significant digits in here, but we need to round this number up. But we did get an extra digit for some reason. We rounded up to 3.68. So that's where if it's 5 or greater, we round up. And if it's less than 5, the last number stays the same. So the same kind of idea. If it's 0.632, we only want to write down 3 significant figures. We're going to just keep it at 6.63. So there are other ways of doing this. Sometimes they have even or odd, where you keep the even number, it remains the same. So if it's 6.677, since this is an odd number, you just keep it at 3.677. If it was 3.676, you would round it up. So I don't like that rule. It's a little confusing to me, and I haven't used it in the past. So for this class, and typically that's the way that we're going to do it in this class. Although, just to know, some people do it differently. Most of the time, 5 or greater, you go up. Less than 5, you stay the same. That's more typically what I have seen. Okay, so we're going to round all of these to 3 significant figures. Just practice this. Use scientific notation where needed, and pause. Take some time to make out scientific notation, round up to the appropriate values, and then we'll move on to the next part. All right, so for this one, if we're going to round this up to 3 significant figures, we can actually make this into scientific notation even though the decimal place is in the middle. Remember, we just want to make a number between 1 and 10. So to make this 3.7459 times 10 to the 1, right, we're going to multiply this by 10. That will give us back to this one. But then we want to round it so to 3. So we want to just look at these 3 digits. We're going to round off the back end. And since this is larger at or larger than 5, we're going to round that number we're going to round that up to 37.5. Since that's 5, we're going to do the roundup rule. For this one, we can generate, we want to do 3 digits. We'll take these 3 largest digits and we're going to drop these off. That number is a 1. We'll drop that off. If we do scientific notation, we go 1, 2, 3, 4, 5, 6. So you can see 5.43 times 10 to the 6th. So that would be our correct answer in scientific notation. Then we're going to do another 3 digits. We'll take those largest 3. We're going to drop off after the decimal place, but we're going to use that decimal place to look at our scientific notation. We go 1 and 2, so times 10 to the 2nd, and we're going to round up because this is 5 or larger. This number 4 here, we're going to go backwards with our decimal place. 1, 2, 3, 4, 8.76. We're going to round this number up because it's larger than 5 or larger, and that's going to be a -4 because remember to recreate this number, we have to make it smaller so that we're going to lose the decimal place is going to go to the left. Finally, we have 7.665. We're not going to use any scientific notation, but to make it 3 significant digits, we go 1, 2, and 3. We're going to round that up because it's 5 or greater. All right, I'm going to spend a little bit more time talking about measurements and how to use them when we start to do some calculations. So this is just to get us introduced to the idea of, hey, if we have a significant figure from one piece of instrument, and then we have to combine that thing. So for example, for density, density is grams, so a weight over volume, usually grams per milliliter. So what if we're using two different instruments to measure these things, and then we have to do some mathematical manipulation of that? So then we want to think about how do we use significant figures appropriately when these are undergoing mathematical calculation. There are a couple rules for doing this, and it depends on if you're doing multiplication and division or if you're doing addition or subtraction. So for multiplication and division, this is pretty easy. You just take the least, so this is where it's important to be able to identify how many significant figures are in a problem. And then you identify if it's multiplication or division or addition or subtraction. If it's multiplication and division, you take the least precise significant figure, and that is what your final answer should be defined as. So here's an example. If I take 10.54, this has 4 significant figures, times 31.4, which has 3, times 16.987, which has 5. Your final answer, you'll take the least precise to the least significant figures. It should be expressed in 3 significant figures. So that will end up with 3 because this is the least precise component of that equation. And then if you throw this in your calculator, you get 5,620. And if we want to put that in scientific notation, we can move the decimal place from here, 1, 2, 3. So we get the 3 significant figures. So really we kind of have to, in this instance, show this in scientific notation to demonstrate it has 3 significant figures, because otherwise you might, well, I guess you'd say there are 3 here, but it's easier to read that there are 3 without that trailing 0. Here's another example of division. So 5.896 divided by 0.008. We have 4 significance here, and remember, if it's behind this decimal place, we don't count it. So this just counts as 1 significant figure. And so we have 1 significant figure. So when we have, we plug this in, we get 700. And we would write that at, if you want to do a scientific notation, to make it simple and clear and easy to see that there's just 1 significant figure, that's how that would work there. So I want you to take a moment, do this calculation, and really what I want you to do is give me the correct number of significant figures. So actually, I'm going to give you some answers here. You don't need a calculator because you should be able to determine what the correct answer is just based on the number of significant figures shown based on the previous slide's rules for doing this. So I'm not actually going to give you the answer to this. If you have a question on how to answer this, this would be a good one to ask the instructor about. So for significant figure calculations with addition and subtraction, this is different than multiplication or division. Now the fewest number of decimal places is where you define the significant figures. So the fewest decimal places. So if I have 2 numbers and I have a bunch of trailing decimal places in this first number, but I only have 1 in this second number, this is the decimal place. This is where the significant figures will be defined then. So I have 4, 1, 3, and these are again the after the decimal places. So because this middle number only has 1 decimal place, that's going to define my significant figure. This is the number that I'll round to in that answer. So 336.9, that's going to be my answer. If I do subtraction, same thing. This first number has 0 decimals, second has 2. My final answer should be expressed with 0 decimal places. So just a little bit of information about significant figures and how to use them appropriately in calculations. So here again, I'd like you to practice based on what we just talked about. I'd like you to practice doing some of these calculations and working through the answers. So pause here, think about what we talked about, and then continue on. So for this, I'm not going to walk through as in detail as I did for some of the other ones, because we're doing addition, so we look for the least number of decimal places, which is 1. For number 2, we have a subtraction, so we want to keep the number of digits that will give us these 3 decimal places, so that is the answer for number 2. For number 3, we're doing multiplication, so we're just going to look at the total number of significant figures, and then we're going to end up with that being the final answer with 3 significant figures. And division, again, we have 4 versus 5, so we'll end up with 4 significant figures for number 4. And finally, if you're doing mixed calculations where you're doing addition and subtraction, typically you're going to do the addition, subtraction first, and then multiplication and division for defining this. Obviously, if you have brackets, or if we're doing other things that, so for example, let me give you an example here. If we're looking at subtraction, we're going to keep the decimal places to that third decimal place for the subtraction, and the multiplication, we're going to keep 2 digits for that. And this is a way to kind of keep track and account for the significant figures. Usually it's a good idea to keep some extra digits so you don't have rounding errors, and then just underline which digit is significant. So we're going to do this group first because it's bracketed, and then this group second, it's bracketed. And then we're going to do a division, and this one has 2, this one has 3. So then our final answer will be presented with 2 significant figures. And just a little note too on exact numbers. I know I'd mentioned this earlier, but if you have something that's counted, or you have a conversion factor here that's 12 inches is equal to 1 foot, for example, those have no uncertainty. We know exactly what the number is, so they have an infinite number of significant figures. So if you think about the rules for subtraction and addition, where you look at decimal places, these don't come into play there, right? So if you're taking 68.35 grams divided by 5, that 5 value, you don't use that for significant digit reasons. So here's an example of looking at this. If we have 36.00 inches that we've measured out with a tape measure, for example, let's say, and we want to convert this into feet, so we're going to take 1 foot is equal to 12 inches. I can multiply this by this conversion factor, and what is going to happen is, again, we're not looking at significant digits, so we take 36 divided by 12, and that answer comes out to be, right, that answer comes out to be 3, but you're going to want to keep the 4 significant digits in this from this initial question here. So 36.00, 4 significant digits. Our answer should be presented in 4 significant figures as well. So the next part of this, we're going to talk about dimensional analysis, and that's kind of using this idea, so this kind of transitions into that, where we're going to use conversion factors to kind of cancel out our units. So we'll talk about doing that. So when we take something, when we multiply a group together, if there's a fraction, these units can cancel out and we get rid of them, and that's how we end up with feet here. So that's kind of the next part, is we're going to now think about using, it's called dimensional analysis, or the factor label method system. And we're going to start off with simple concepts to kind of show this idea, but then once we go through the semester, we'll be kind of combining things. It'll be a little more, it'll get more and more complex. So learning how to do this is important, even if you maybe have a feeling you have a way to do this, or hey, I can just like look up how many feet are 36 inches. I can just do that with my calculator. But again, this is a technique that I'm trying to teach you so that you can apply it to other more complicated things where there's not going to be a simple way to solve or to find the answer with an app or a calculator conversion system.